Thank you so much, Christian, for the kind introduction, and thank you to the organizers. I'm really thrilled to be here. So today I'm going to talk to you about the central role that communication networks play in designing robust blockchains. So a lot of the literature on blockchains involves trying to enforce one or more of several properties that we might like to enforce. And these properties include things like security, performance, privacy, and fairness. And this is, of course, an incomplete list. It's a list that was crafted for the purposes of my talk, but there's obviously other properties that people may want to enforce. So in practice, when we design blockchain systems, how do we ensure that our systems satisfy these different properties? Well, there's a number of different techniques that people typically take. But in general, the classical approach has been to design algorithms at the application layer, meaning we design new consensus algorithms, for example, that provide some kind of order fairness, just to give an example. And the observation that I would like to emphasize in this talk is that blockchains run on communication networks. And these communication networks are often overlooked, somewhat overlooked in the classical blockchain literature. And by overlooked, I don't mean that they're completely ignored, but I mean that we model them in a fairly coarse-grained way, like this black box that just has certain properties. And so the question that I would like to ask here is, what can we do when we think more carefully about how these communication networks operate and how they impact the application layer performance? So this talk will be about how to incorporate the design of the peer-to-peer network into blockchain design. And in particular, I'm going to talk about this in terms of three ways of incorporating this information. The first way is by actually modeling the network at a more fine-grained level than what's typically done. The second layer is actually analyzing how these peer-to-peer network models impact the final performance. And the third aspect is, can we actually redesign the network itself to better impact our end application layer performance? So these are the three techniques that I'm going to look at, and I'm going to look at them in the context of three of those properties that I mentioned earlier. The first one is performance, and here I'm lumping performance and security together because you don't want one without the other. The second property is going to be privacy, and the third one is fairness. Okay, so let's get started. All right. So I assume, given the audience, probably many of you are already familiar with this, but just for completeness, I'm going to start by talking about how Bitcoin implements its peer-to-peer layer. Okay, so a lot of most permissionless blockchains have some kind of peer-to-peer network that nodes use to communicate with each other, and the Bitcoin network structure has been widely adopted by many blockchain systems. So the idea here is that nodes are connected to each other in a peer-to-peer network of TCP links. And nodes are also identified both by their IP address and by a public key. And similarly, transactions are also identified by their public keys. So whenever Alice wants to send money to Bob, the first thing she does is to compose a transaction in plain text that says Alice, identified by her public key, is sending money identified by its public key to Bob, identified by his public key. And this information then gets flooded over the peer-to-peer network until all of the other nodes in the network receive this message. So what role does the peer-to-peer network play? Well, it governs the dissemination of transactions and blocks. And so in this sense, it's a necessary condition for us to achieve something like consensus. And currently, many cryptocurrencies implement their peer-to-peer network in such a way that we can effectively model this flooding process by what's called a diffusion process. So in other words, as your message spreads, the delay that it takes for your transaction or block to reach one of its peers is pretty well modeled by an exponential random variable. And different delays are independent of one another. Okay, so we call this a diffusion process. That's a pretty good model for peer-to-peer spreading mechanisms today. And as we're going to see in this talk, this property has implications both for performance, privacy, and fairness. So let's start by talking a little bit about performance. Okay, so this is going to be based on work with a number of awesome collaborators. And in particular, I'm going to focus on two papers that came out of this line of work. Okay, so when we talk about blockchain performance, how do we actually measure it? Well, there's two main metrics that people typically use. The first is transaction throughput. So how many transactions per second are we able to process? And the second is confirmation latency. So how long does it take to actually confirm a transaction? And today there's literally a zoo of different consensus protocols that operate at different points on this chart. And so a natural question to ask ourselves is, what is the best that anyone could hope to do in terms of these two metrics? So one natural fundamental limit on confirmation latency is the speed of light delay, which I'll use D to denote this. So this is the time it takes for a message to physically get transported from one point to another according to the speed of light. So can't go faster than that. Another natural fundamental limit on transaction throughput is the capacity of our network. So how many transactions per second can we reliably deliver? So ideally, we would like to be at this operating point where this yellow dot, okay? And so this portion of the talk is going to be about our efforts to approach this yellow dot. So as I mentioned, a big portion of the approach here, both in this section of the talk and the others, is to look more carefully at what exactly the peer-to-peer network is doing. So remember, we said that our networks exhibit this kind of flooding mechanism to transmit both blocks and transactions. So in this work, we modeled the network as follows. We let C denote our network capacity, so the number of transactions per second that our network is able to communicate. And I'll remind you what this notation means later as it becomes necessary. And D is going to be our speed of light propagation delay. Now, our total network delay, so the total amount of time it takes for a block to start from one node and reach all of the other nodes in the network, we modeled as the following expression. So first we have our speed of light propagation delay summed with an additive term that grows linearly with block size. And here block size is measured in number of transactions, how many transactions per block, and scaled by the network capacity. Okay, so this formula is pretty simple, but was based on empirical measurements from a while back, and is already a more nuanced model of the network activity than what we typically see in papers on new consensus protocols. Okay, so this is our model for our peer-to-peer network. So overall, our model has this network delay property. We also assume that our adversary controls a fraction beta less than a half of computational power in our system. Adversarial nodes need not follow protocol, and adversarial nodes can communicate instantaneously among themselves. So they're not bound by this network model that I mentioned earlier. So mining, we assume that blocks are mined as a Poisson process with a rate proportional to the fraction of computational power that you hold. Pretty standard assumption. And we define confirmation as an event after which the transaction cannot be reverted with probability more than epsilon. Okay. So this is our definition of, so latency is basically the time that it takes to reach this confirmation state. Okay. Now, based on this model, we can start to revisit these fundamental limits that I talked about earlier. So in particular, I want to look at two plots. First one is throughput as a function of adversarial fraction beta. Okay, so we said that throughput can never be higher than our network capacity, but we can actually say something slightly more nuanced, which is that as our adversarial fraction grows, our maximum throughput must also decay linearly because we can't force the adversarial nodes to contribute to throughput. Okay, so this is an upper limit that we cannot surpass. At the same time, we can also look at lower bounds on latency. So no matter what reliability epsilon we want, our latency is always lower bounded by the speed of light delay, d. Now, it may be possible to get tighter lower bounds for certain regimes, but in general, this is always going to be a lower bound. Okay, so now given these fundamental limits, it's useful to first take a look at how Bitcoin, how Nakamoto Consensus fares compared to these upper and lower bounds on throughput and latency, respectively. And then we'll talk about how to actually approach these fundamental limits. So let's start with a quick recap of Nakamoto Consensus, longest chain rule. So as I believe probably most of you know, whenever Alice generates a transaction in Nakamoto Consensus, the first thing that happens is that she broadcasts it to all of the other peers using that flooding mechanism we talked about earlier. Then these peers, or the miners among them, will start trying to mine blocks. Okay, so the transaction eventually appears in a block, after which new blocks are mined by the same miners. Okay, and the key factor in Nakamoto Consensus is that if we ever have a situation where one chain is longer than the other, the miners will choose to build on the longer chain, hence the other name longest chain rule. Okay, and so our confirmation rule here is that we're going to treat our transaction, Alice's transaction, as confirmed once it is buried k blocks deep into the longest chain in our blockchain. Okay, and here k should be chosen as a function of the desired reliability epsilon. Okay, and recall from the previous, or from our model slide, as long as beta less than a half fraction of nodes are corrupt, or fraction of hash power is corrupt, transactions cannot be reversed except with probability epsilon, at most epsilon. So that's our definition of confirmation, and we're choosing k such that this property holds. Okay, so this is Nakamoto Consensus, and the key observation here is that in Bitcoin, blocks play two roles. First role is adding transactions to the blockchain. Okay, so when Alice first proposed her transaction, we needed a block to be mined so that that transaction could actually appear somewhere in the blockchain. Second role is actually voting on prior blocks. So every subsequent block that gets piled on top of the first block is like a vote of confidence saying, I believe that all of the previous transactions in this chain are valid. So it's implicitly a vote of confidence in Alice's transaction. Okay. So how does this dual role of blocks affect performance? Okay, and we're building up to showing how those fundamental limits compare to the performance of Bitcoin. Well, okay, the problem is that in order to achieve security, in order to achieve our definition of confirmation, we need to have a low mining rate. Okay, and a low mining rate means that we're adding transactions slowly to our blockchain, which in turn means that we're getting low throughput. At the same time, this low mining rate implies that we also have a low rate of voting on prior blocks. So it takes a long time for a transaction to get sandwiched k deep in the blockchain. So this in turn leads to high latency. Okay, so both of the functions of both of our performance metrics are suffering as an effect of requiring, as a result of requiring a low mining rate, which is happening because we need security. Okay, so a very natural question to ask is, well, why can't we just increase the mining rate? And the problem here is that if we increase the mining rate, everyone starts producing blocks faster, and these blocks start conflicting with each other. So they may have the same parent. And in these cases, ties are broken by the miners. And we end up with the honest miners creating a block tree that is much wider than it would be if we had a slow mining rate. Now, the problem is that at the same time, the adversary also gets to produce more blocks. But because our adversary is not constrained by the network, so we assume that the adversary can communicate instantaneously among its nodes, the adversary can actually stack all of its blocks sequentially. Okay. So this forking in the honest portion of the blockchain is happening because of network delays, but the adversary is not constrained by these network delays. So increasing mining rate trades off efficiency for security. So this is not a desirable trade-off. So as a result of this, actually, we can look at how Nakamoto Consensus performance scales with various parameters of our model. So if we go back to these fundamental limits we talked about earlier, you can show that Bitcoin's throughput is upper bounded by something that looks like this red curve. And actually, Bitcoin today operates at this very negative or very low throughput operating point, which is indicated by the red dot. Okay. And in terms of latency, we see that Bitcoin's latency is scaling up very quickly with a slope that looks like the speed of light delay of blocks. Okay. And this is happening because we need to wait for K of those blocks to pile up before we can actually confirm. Okay. So, all right. So what's the reasoning for this? How can we get around this problem with Bitcoin? So in this work, we proposed a system called Prism, which tries to tackle these problems by actually separating those two roles of blocks that I talked about earlier. The first role of blocks is mapping transactions into the blockchain. Okay, so that's going to be the first portion of our system design. And the second portion is actually confirming blocks once transactions have been inserted into a block. Okay, so the key idea behind Prism is to separate these two functionalities into different mechanisms so that we can scale up one without affecting the other. Okay, so how do we do this? Well, Prism has different types of blocks. The first type of blocks is called transaction blocks. Okay, and this is where we're going to store all of our transactions, as the name suggests. So we're going to generate transaction blocks at a very high rate. And this is, as I mentioned, where transactions are stored. So by generating these at a high rate, this is how we're getting high throughput. Okay. At the same time, we have an anchor set of blocks called the proposer tree. Okay, so these blocks are produced at a slow rate. And these proposer blocks have the role of containing pointers to transaction blocks. And a pointer to a transaction block just means I think all the transactions in this transaction block are valid. Okay. So again, like the longest chain protocol, you can have multiple proposer blocks at the same level. And ties here are broken, again, according to longest chain. Okay. So the proposer tree grows like this. And the key observation here is that even though this proposer tree is growing according to longest chain rule, we're not taking just the longest chain of these proposer blocks. So in fact, it's possible that we consider at each level one proposer block for example, we could consider this top proposer block to be valid, and then we could consider this forked proposer block to also be the valid proposer block at the next level, and then move back to the longest chain. Okay, so we're not constrained by the longest chain rule to validate these proposer blocks. So to achieve this, we need the third component of Prism, which is a set of what we call voter trees. So the idea behind this is that we have a bunch of different longest chain voter chains, which are voting on the proposer blocks or the blocks in the proposer tree. Okay. So the job of each voter tree is to cast a vote at each level of the proposer tree on one of the proposer blocks. So for example, here in the beginning, we have only one block at level 1. So all of the voter trees are going to vote for that one block. Now at level 2, we have 2 proposer blocks at this level. So now voter trees have to make a choice. They can either vote for one or the other, or potentially if there's malicious nodes, they could vote for their own private block, proposer block that has not been released yet. So here in this example, we have 2 voter trees that are voting for the block on the right and 1 voter tree that's voting for the block on the left. Okay, and then by majority vote, we're going to take the block on the right as the canonical proposer block for this level. And we proceed like this. Okay. And notice that because these voter trees are growing according to the longest chain rule, you can have forks. And these forks are resolved just as they would be otherwise with the longest chain rule. Okay. All right, so to understand why this is useful, I want to talk very briefly about our confirmation rule. So really, these voter trees are doing the job of confirming our transactions. So what is the confirmation rule exactly? Well, let's start with a very naive version of the confirmation rule. So in a naive version of the confirmation rule, we would wait for all of the voter trees to vote on one of the blocks, let's say at level 2 of our proposer tree. Okay. Now we know that in order for the voter trees to stabilize their votes, we need to wait for each of these votes to become K deep. Okay, that's from Nakamoto Consensus. So we could wait for each of these voter trees to have their votes embedded K deep into the blockchain. But the problem is that if this happens, if we wait for this, our latency is going to be no better than it was with Nakamoto Consensus. In fact, it'll be worse because we have to wait for all of these voter trees to vote. But the key insight of Prism is that by having many, many voter trees, so think like 1,000 of them, we don't need each of these votes to be completely stabilized before we can call the race. Okay, so in particular, we could allow each of these votes to be to have some probability of reversal that's larger than epsilon, and still be confident that the majority vote will not change. So here we're using a law of large numbers kind of rule to call the race once block B, for example, has built up enough of a lead compared to block A, such that we can be 1 minus epsilon confident that the majority vote will not switch. So that's the key idea. We're using law of large numbers where the large numbers are taken over the number of voter trees that are stored. Okay. And I want to emphasize here that all of the nodes are storing all of the chains here. It's transaction blocks, proposer tree, voter trees. So it's not like we're partitioning the nodes into storing different portions of the blockchain. Everyone's storing everything here and is mining on everything. Okay, so the main result here is that by using this law of large numbers insight, we can actually achieve within a constant factor of this upper bound on throughput. Okay. So, and at the same time, if we look at the results for latency, we can see that Prism achieves within a constant factor of D for a much larger range of reliabilities or epsilon values. And in fact, we see a transition point here when we hit an error probability that looks like the bandwidth delay product. Okay? And once that happens, our confirmation delay starts growing at a slope of 1 over C, where C was our network capacity. So if we compare this with Bitcoin, C is a pretty big number. We can think of like 100 Mbps, for example, as like a lower bound probably. So, so this slope is actually quite modest in practice. And theoretically, in this region, below the bandwidth delay product, we're within a constant factor of our lower bound. So the main result is that if our adversarial hash power beta is less than 1/2 and the reliability epsilon is exponentially small in the bandwidth delay product CD, Prism is guaranteed to confirm honest transactions with a latency proportional to D and eventually confirm all transactions. It also achieves order optimal throughput proportional to 1 minus beta times C. So we ran a full empirical comparison of Prism compared to some other, at least academic implementations of consensus protocols at the time this was done. So we compared here to Algorand, Bitcoin protocol, so longest chain, and Bitcoin NG. And so here, sorry, the axes are flipped. Here, throughput is on the vertical axis and latency is on the horizontal axis. So we want to be up and to the left. And so these red plus signs are the Prism performance. And so here, as you change your adversarial fraction, beta, different protocols may have different trade-off or operating curves. So that's why you're seeing beta specified everywhere here on the plot. But basically what we see is that Prism is able to achieve quite high throughput. This is on 1,000 nodes on an AWS network of 200 Mbps with a delay, an end-to-end network delay of about 2 seconds and a forking quantity of about 0.1. So we're able to reach throughputs that are many orders of magnitude higher than Bitcoin and latency that's about 2 orders of magnitude lower than Bitcoin's, but it's also outperforming these other, at least academic implementations at the time this was run. So the take-home message here is that by modeling and analyzing the network more carefully, it illuminated some otherwise hidden performance bounds and also allowed us to, or like helped us think about how to design protocols that account for real network dynamics. And this led to the performance gains that I was showing on the previous slide. One of the big downsides is that Prism is substantially more complex than longest chain protocol. I think one of the reasons longest chain is so cool is that it's such a simple protocol. So I would say that's probably one of the main drawbacks of Prism compared to even other later consensus protocols. Prism is being considered for adoption by the Mantis client in Ethereum Classic, but I'm not sure how far along that is. So, so that wraps up the first portion of my talk on how to incorporate the peer-to-peer network, where we talked about how modeling the network and analyzing the effects of the peer-to-peer network impacted performance. So before I go on to the second part, are there any questions?
Maybe I don't want to interfere too much, but how do you compare the security levels of, you mentioned earlier more the throughput and so, but how do you compare the security levels? Can they put on the same?
Right, so all of these, sorry about that. Yeah, all of these curves are plotted for the same security level. Here we chose epsilon 10 to the minus, I want to say 10, but I'm not 100% sure about that, sorry. But we did control for that. Yeah.
Well, thank you.
Any other questions? I think I saw a hand, but I can't see right now who it was. You just want to unmute yourself. Okay, well, if you think of anything, we can.
Yeah, hi, I'm François. I'm wondering, there's a cottage industry of DAG-based consensus protocols that take this approach of having multiple proposers at the same time for fragments of a block. In this lineage, you would find things like Hashgraph, Blockmania, Aleph, but there's a long history of those, and they have typically different network characteristics, including relatively high dropouts. Have you run a benchmark against any one of those protocols? Do you plan to?
That's a great question. We have not run, we have not run any comparison against those protocols. How did you say their networks differ? I didn't quite catch that.
So I'm talking about a class of protocols, so it's really difficult to describe them at the level of abstraction suitable to encompass all of them. But the general idea is that they all, so each node proposes block simultaneously. They can have a synchronicity or partial synchrony if you're depending on which protocol we're talking about, but votes are then collected on each of the blocks nodes. So they intensely rely on a gossip network for everybody to be aware of everybody's proposals, but votes are simultaneous on proposals from multiple proposers. They carry a lot of similarities in network communication patterns to either taking a classical BFT algorithm and having everybody run it at the same time, or your tree proposal.
Yeah, so I mean, I think their model is definitely comparable and can be captured by the network model that we're looking at. Our criterion for which protocols we decided to implement against was basically going through the last couple of years of academic conferences and papers and looking at the implementations that were released in association with those. So we didn't look, I mean, there was a lot of protocols that, excuse me, that also have this property of, like you said, multiple proposers working at the same time. There's a lot of similarities between what you described and the way the Prism protocol works. But we wanted to, yeah, just for the sake of this evaluation, we looked at papers that were peer reviewed and had public implementations, and that was kind of the main criterion that we used. So we haven't looked at any of done a comparison against any of the protocols that you mentioned.
Okay.
Anyone else?
Thanks.
Oops, sorry. Okay. All right, so I will go on then. Okay, so in the second part of this talk, I'm going to mention how looking at network design can impact privacy. So if we recall from before, we have this figure of Bitcoin's network dynamics, which shows the peer-to-peer network as a flooding network. And this network basically impacts or has some impact on the privacy properties of our blockchain protocols. So how do we usually think about privacy in blockchain networks? Well, traditionally, we've thought about privacy at the application layer, meaning can an observer link public keys to human identities? Okay, so the idea is that we want to be able to take a transaction message, and link it to Alice's human identity. So there's been a whole ton of work on using public blockchains to link transactions both to one another, and in some cases, even to the human identity of a sender. So this is just a couple of papers, but there's really been a huge amount of work. So there's also been a smaller line of work on understanding the privacy properties of the network layer. So here, the question is, instead of trying to link a transaction to a human identity, can we link a transaction to an IP address? So here, instead of figuring out that this transaction belongs to Alice, we're trying to figure out that it belongs to Alice's IP address. And there were some early papers that show that this is quite possible. So how does this happen? So the key idea behind the work that I'll talk about in this portion is based on, first of all, modeling and analyzing the probability of this happening, and also trying to redesign the peer-to-peer network to make this more difficult. So let's start by talking about what kind of adversarial model should we be envisioning here. So a lot of the practical attacks that we have seen in the security literature use a model that can be very coarsely approximated by the following. So we assume that some fraction of the nodes in the peer-to-peer network are spies. So these are the nodes who are trying to de-anonymize. Their identities are unknown, and they observe all metadata in the network, and they collude with each other. For our initial analysis, we assumed that they were honest but curious, but then we did some follow-up work to relax this assumption. So how can this kind of botnet adversary actually break network privacy? The key idea is that these spy nodes, which in this picture are indicated by the red nodes, can use knowledge of the network topology and timing and other metadata to infer the source node of a diffusion process. So remember, we said the spreading of transactions can be modeled pretty well by a diffusion process. So there's been a ton of work, both theoretically and empirically, showing that this is possible. Okay. So the idea is these spies collect some timing information and use knowledge of the graph to infer the source. So in our work, we were trying to design a different networking protocol that makes this kind of inference difficult. So in particular, our metric for anonymity here was dual. We used both recall and precision. So here there's some number of users, n users, each of which is generating some number of transactions. And the adversary's job is to design a mapping from transactions to users. And the adversary is trying to maximize its recall, which is basically the probability of detecting or associating a transaction with a true originator. And the other metric is precision. So precision is basically penalizing mappings that map all of the transactions to the same user. So precision is reflecting the fact that we know all of these transactions are not originating from the same user. So our goal here is to design a distributed flooding protocol that minimizes the maximum precision and recall achievable by a computationally unbounded adversary. So briefly, the spreading protocol that we designed is called Dandelion. So if we assume that the source node is this node here on the far left, Dandelion has two parts. In the first phase, the transaction is spread over a random path, which we call the stem phase. Okay, so the stem phase lasts for a random number of hops. And eventually, we transition to what's called the spreading phase. And here, the transaction is just diffused over the rest of the network. Okay, and it's so named because the spreading pattern looks like a dandelion seed head. So why use dandelion spreading? Well, we can show that dandelion spreading has an optimally low maximum recall. So in particular, we show a lower bound on the maximum recall of P, where P is the fraction of spy nodes in our network. And we can see that Dandelion has a maximum recall that is within a factor of 1 over n of P. Okay. So that covers recall. Basically, this means the only thing we need to worry about is what is the topology over which we're running this Dandelion spreading. And to cover this, Dandelion is run over a line graph. Okay, so basically, we have two portions of our peer-to-peer network. We have an anonymity graph, which is indicated by the black lines here, and the regular graph, which is just the usual TCP links indicated in blue. So when a transaction comes in, it is spread clockwise over the black graph, over the anonymity graph, until it transitions to the spreading phase. And then it diffuses over the blue nodes or blue edges. Similarly, if a second transaction comes in later, it propagates clockwise over the same black cycle graph or line graph, and then diffuses over the blue edges. Okay, so the fact that these are using the same cycle for the anonymity portion of, or for the stem phase is important. So to summarize, the Dandelion network policy involves using Dandelion spreading over a line graph or a cycle graph. Okay. And under these two conditions, we can show that Dandelion has a nearly optimal maximum precision. So here we show a lower bound of P squared. Again, P is the fraction of spy nodes in our network. And we achieve within a logarithmic factor of that. Okay. So for the sake of time, I'm going to, not spend too much time dwelling on this, but This is a figure from a paper from 2017 that showed various privacy and confidentiality technologies that were proposed. And the yellow ones here are the technologies that got adopted in Bitcoin. The blue ones were the ones that got used in altcoins, and the gray ones are the ones that got not used at all. And so the kind of striking thing about this figure is that the technologies that tended to get adopted by Bitcoin are the ones that have weaker privacy guarantees. So they're based on obfuscation rather than cryptography. So kind of at a meta level, our approach with Dandelion was to max out the guarantees we can get with obfuscation without veering into the territory of cryptographic protections. So I think today, Dandelion has been implemented in a number of altcoins, so most notably Monero. It's being considered for a few more. I think Zcash has a proposal looking at it, and I'm not sure if it's still under consideration for Bitcoin, but it was being considered at one point. So we're kind of straddling that boundary at the moment. So that's just a very quick overview of how we can use finer grained modeling of the peer-to-peer network to both understand how attacks can happen and to revamp the peer-to-peer network in order to make attacks more difficult. Okay, so in the last couple of minutes, actually, yeah, I guess since we can go ahead and do a couple of questions here if anyone has questions they want to ask.
There is one question in the chat, but it's for part one, so we can also take this in the end.
Okay, sure, let's do that. Okay, and in the last portion of, so far we've talked about how to use the design of the peer-to-peer network to improve our understanding both of performance and of privacy. So in the last portion of the talk, I want to very briefly touch on a problem that we've been looking at just recently. This is work in progress, but we've been looking at the problem of fairness. Okay. So when I say fairness, I really am thinking about the problem of front running. So front running is a problem that has emerged pretty significantly in the last couple of years, especially with the popularity of decentralized finance protocols. And the idea is that if you have multiple users who are participating in decentralized finance protocols, if one of them transmits a transaction over the peer-to-peer network, so let's say Alice here is our victim, and she broadcasts that she wants to buy one token of Uniswap, Bob may be able to see that fact over the peer-to-peer network before Alice's transaction actually gets mined. So when Bob sees this transaction, he can suspect, okay, once Alice's transaction gets processed, the price of Uniswap is going to go up. So Bob proposes his own transaction with a higher transaction fee, and the miners, being rational, are going to process Bob's transaction first. Okay, so they process Bob's transaction, the price of Uniswap goes up. Then they process Alice's transaction, the price of Uniswap continues to go up. And then Bob sells the Uniswap that he bought, making a profit for himself and more importantly, costing Alice because she made her order when she thought the price of Uniswap was different than what it actually was. Okay, so this is a problem that has received a lot of attention in the last couple of years, and in particular, it's something that people have been looking at the consensus layer. So in the last couple of weeks, months, we've been looking at what role does the peer-to-peer network play in this front-running problem. So basically, let's think about a network where we have our victim node, so Alice here is in yellow, and a front runner who is placed in between the victim and the miner. Okay. So our sequence of transactions here looks like this. Our victim sends transaction TX1. Meanwhile, our front runner hears about transaction 1 and generates a competing transaction TX2 with a higher fee. And okay, here I've drawn this graph as a tree. So the front runner can actually just drop Alice's transaction or relay it later whenever he wants. But the miner now chooses the transaction with the higher fee. Okay, so Bob or the front runner here has the opportunity to front run Alice based solely on having an advantageous location within the peer-to-peer network. So a natural question to ask is, how can a front runner manipulate the peer-to-peer network to improve chances of success? So are there active strategies that front runners can adopt in order to improve their success rate? And as system designers, can we make this difficult? So we've started looking at this problem just from a theoretical standpoint. So we assume that the adversary is given the structure of the peer-to-peer network and is allowed to add up to M links to the network. And the question is, how should the adversary add these links in order to maximize their ability to front run other nodes? Okay. So, so this is kind of a graph design problem. Some of our early results, as you can probably imagine, this problem ends up being NP hard. And you can show this through a reduction from set cover. And you can also see that greedy approximations are arbitrarily bad. So you cannot approximate the optimal solution within any constant factor. We've also started simulating some of these strategies, some simple strategies for adversaries to improve their location in the network and improve their ability to front run. And we find that some fairly simple strategies actually do pretty well. So there was an interesting paper from 2020 called Carnegie that was actually designed to improve peer-to-peer network latency, broadcast latency. But it turns out that by adopting this Carnegie strategy, nodes can actually front run one another better if the rest of the nodes are not adopting Carnegie. So that's kind of an interesting, maybe unintended side effect. Okay, so I've talked long enough. So that kind of wraps up the 3 portions of the talk that I wanted to touch on. So we've seen how to use a more nuanced model and analysis of the peer-to-peer network to improve blockchain performance, privacy, and fairness. So the take-home message here, I think, is really that the communication network plays a central role especially in public blockchains, maybe less so in permissioned ones. And modeling and analyzing these effects can actually give pretty substantial gains compared to just looking at the application layer. So with that, thank you all so much for your attention, and I'll be happy to take more questions.